Hello everyone. In this session we will discuss one new module, that is module number 3. As per your syllabus, the module number 3, it is Kani's method. Okay. So the Kani's method is another method of analysis. So this method, as per your syllabus, we use this method to analyze the indeterminate structures. So if you go with the basic methods or the previous two methods which we have studied, one is slope deflection method and another one is the moment distribution method. So in the slope deflection method, we have discussed that method in detail, and we know that in the slope deflection method we will develop some of the simultaneous equations and we solve them to determine the unknown rotations. Using those rotations we use to determine the end moments, and from the end moments further process. But if the slope deflection method is used to solve bigger structures like multi-story frames and all those things, in those situations the number of simultaneous equations developed are very high. So we cannot solve manually the more number of simultaneous equations. So that will become very difficult. So to avoid that, what people have done is people have developed the other methods like moment distribution method. And similarly, this Kani is also one of the such method which avoids the solution of the simultaneous equations. Now, this method it was developed by a person called Dr. Gaspars Kani. The name of the scientist who has proposed this method is Gaspars Kani. Based on his name, the method is also named as Kani's method. He is from Germany. Okay. And this method was developed in the year 1947. So this method is developed in the year 1947 in the Germany by a person called as Gaspars Kani. And this method is based on rotation contribution. Contributions. We will discuss what exactly meant by the rotation contributions and how to estimate the rotation contributions. All those things we will discuss in detail. Okay. This is one of the oldest method used to analyze multi-story frames. As I said earlier also, use of slope deflection method for the bigger structures is difficult. So to avoid that, so people have come out with this method. This method is also an iterative procedure like moment distribution method. As we go for the iterations in the moment distribution method to determine the final end moments, so the similar way here also we will be doing some of the iterations to achieve the end moments. Okay, I hope you remember the slope deflection equation which we used for the analysis of the structure in the module number 1. So in just remind of that, see here, the slope deflection equation for a span AB, that is if I want to determine the moment M AB, then the equation which we used is MF AB plus 2 EI by L into 2 theta A plus theta B minus 3 delta by L. This was the standard slope deflection equation which we have used to determine the end moments as per the slope deflection method. So, let us say if for any span, if the sinking is 0, then this last term, that is 3 delta by L, goes to 0. Now, if I rearrange this, we will get, see, MFAB plus, if I multiply this inside, so it is 4 EI by L into theta A plus 2 EI by L into theta B, right. So, here the term 2 EI by L into theta. So, this term, it is nothing but moment due to rotation at any joint, that is called as rotational moment, or it is also called as the rotational contribution. So, this, that is 2 EI by L into theta, this term, it is nothing but the moment developed at any end due to the rotation of that particular joint or that particular end. So, this is called this moment is called as the rotational moments. So, Kani has used this rotational moment or this rotational contribution in the procedure or in the calculation, and he has come out with an iterative procedure where we can handle more number of unknowns or we can deal with the bigger structures, right. Okay. So, now here I will take a small example and will try to explain the concept in detail. Okay. See here, if I have a continuous beam, let us say this is a continuous beam where we have two supports, let us say this is A and B supports, which is loaded with some 2-point loads, random loads, let us call them P1 and P2, right. So, because of this loading on the span AB, the span AB will undergo the deformation. Let us assume an deformation something like this, okay. Because of the loading, let us assume that the beam has undergone a deformation something like this, okay. So, let us call the rotation at this joint as theta A, similarly the rotation at this joint as theta B, okay. So, this rotation will remains same, this is also as theta B, okay. So, because of this loading, there will be a development of the moments, okay, at the ends. Let us say these are the end moments MAB and this is MBA. So, our intention is to determine these end moments MAB and MBA. So, MAB and MBA are nothing but the end moments at end A and at end B. So, we need to determine how much is these end moments. So, that is my intention. So, if I see this in detail or in parts wise as per the slope deflection method, we can divide or we can categorize this into the many different situations. Like, see, for example, if I take only these span, okay, if I take only these particular span, so there is a development of fixed end moments at the ends. There is a development of fixed end moments at the end due to these external loadings, that is P2 and P1. So, let us say those end moments are MFAB, MFAB and MFB. So these are the fixed end moments developed at the ends A and B due to the external loading. So here we are not worried about what are the actual support conditions, we are assuming that both ends are fixed. This is one situation. Next, if I take another situation where the rotation is happening only at the end A, that is this where second situation where the rotation is allowed only at end A here, end A and end B. Because of this rotation, let us say, because of this rotation, okay, let us say here the rotation is theta A. Because of this rotation, there is a development of moment here as well as some moment here. Now we need to think here how much is the moment developing at end A and end B because of the rotation at A. So here this much is the rotation, that is 4 EI by L into theta A. That is the rotation developing at the end A because of the rotation at the same point A. So let me call this as, that is the rotational moment as m, small m, okay. So it is on the same point, so it will be 2 times, that is 2 m AB, that is the rotational moment developed at the end A, because here it is 4 EI by L. 4 means it is, that is if I take the 2 EI by L into theta A as the m, then 4 it will be 2 EI, 2 and 2 rotational moments. So obviously this will be half of this, that is theta B, as it is on the other end. So here I will write it as, it is m AB, half of that, okay. So this is the second situation where the rotational moments are developing at the end due to the rotation at the end A. Similarly, we have another situation where the rotation is allowed at the end B, at this end, okay. You can see, so this is the rotation allowed. So here this is theta B, this is end A, this is end B. Because of this rotation, there is a development of the moments at the ends. So in the similar way, this will be 2 times of MBA and this is 1 times of MBA, right. Now if I want to determine the final end moments because of all the different individual cases, then what I need to do, I need to take the sum of these values, that is final end moment at A, that is MAB is equals to MFAB plus 2 times of the rotational moment at A, that is 2 MAB plus 1 times of MBA. So here I can write here is the MAB is equals to, it is MFAB plus the rotational moment, that is 2 times of MAB plus this rotation moment, that is MBA. Similarly, MBA is equals to, that is final end moment at B, MBA is equals to, it is MFBA plus I will write this one, that is 2 times of MBA plus MAB. So these are the final end moments which we use to determine. What I have done here is I have taken the same slope deflection equations without sinking. and modify them in terms of the rotational moments. Now, the final end moments MAB and MBA, they are read in terms of fixed end moments plus the rotational moments. That is the rotational moment at end A, and this is the rotational end moment at B. Right? So, the same thing, but the interpretation has become different. Right? So, now based on this, the Kani has developed the further procedure. So, before that, I would like to discuss one more thing or one more topic in detail, that is called as the rotational factor. As like we have the distribution factor in the moment distribution method, the similar way we have one more factor here, that is called as the rotational factor. So, I hope you know how to calculate the distribution factor. In the same way, exactly same way, we have to work out one more factor here called as the rotational factor. Okay. So, let us see what is the rotational factor in detail. Rotational factor. So, to discuss or to tell what is the rotational factor, I would like to consider one frame. Okay. So, let us say we have a multi-story frame here. Okay. Right. So, okay. So, let us say this is joint A, this is B, C, D and E. I am not naming all the joints, these are the only 5 joints which I required, so I have named only those 5. Okay. Now, let us say the joint A has undergone a rotation. Okay. It has undergone a rotation due to some external loading conditions. So, if I assume the joint A has undergone a rotation by 1 unit, okay, so then the deflected shape of the beam AB, AC, AD and AE will be something like this. Okay. So, these are the end moments, so we have to consider them as fixed. Okay. Right. Okay. So, now the joint A has undergone a 1 unit or it has gone the rotation. So, because of this rotation, there will be a development of bending moments at the ends of each span. That is, there will be a development of bending moment here as well as here, here, here. At all the locations, there will be a development of bending moment. So, let us say this as, let us call this as MAB, right. Similarly, there will be a development of moment here MBA, which is I am not worried at this point. So, similarly at this location there will be a development of a moment called as MAE. So, here also there will be a development of moment MAD. So, here there is a development of another moment called as MAC. So, these are the bending moments which develop at the in and around the joint A. So, I am worried about all these 4 moments. Okay. Right. So, as per our modified equation for the bending moment, so what are the equations? So, if I want to determine the bending moment at A, that is MAB, so this equation will be, it is MFAB plus 2 times of the rotational moment, that is MAB, plus the other end moment, that is 1 times of the MBA, right. So, this is the modified equation for to determine the moment at any end. Similarly, if I want to determine MAC, so this will be MFAC plus 2 times of MAC plus 1 time of MCA. And similarly for the MAD, it is MFAD plus 2 times of MAD plus 1 time of MDA. And lastly for MAE, it is MFAE plus 2 times of rotational moment MAE plus 1 times of MEA, right. So these are the end moments at the joint A. These are the 4 moments which are developing due to the rotation of the joint A. Now we also know one more thing, that for equilibrium position or the equilibrium of the joint A, if you take the sum of all the moments at any joint, then the total sum should be 0. That is, for equilibrium of joint A, the summation of moments at joint A must be equals to 0. If I take the sum of all the moments at joint A, then the total sum should be 0. Now here at joint A we have 4 members, means I have to take the sum of all the 4 members, that is the MAB plus MAC plus MAD plus MAE. The sum of all these 4 moments should be 0. Now if I take the sum here, what happens? See, I have to take the sum of all these things. So what I will do, I will write in a modified way, that is sum of fixed end moments near the A, that is MFAB, MFAC, MFAD and MFAE, that is the summation of fixed end moments at joint A. Might be it is MAB, MAC, MAD and MAE, like that, okay, plus 2 times of, okay, 2 times of these values, that is the moments nearer to the A point, rotational moments due to the rotation of the joint A, very close or very nearer to the end point joint A, that is 2 times of the summation of rotational moments at A. So let me call this as M dash, okay, then plus the summation of M double dash. What is this? What is M dash? M dash is nothing but the rotational moments near at near end, and M double dash is rotational moment at the far end. See here, M dash AB, this is rotational moment here, MCA, so this is rotational moment at here, MDA at here, so it is far end. So that's why I have taken it as M double dash, algebraic sum of all the far end moments. So this total should be, this sum should be equals to 0, right. So now here what I am is, I am interested in calculating how much is the rotational moments, that is algebraic sum of rotational moments at the near end. So if I take that outside, that is 2 into summation of M dash, this is equals to, if I take it everything on the other side, it will be minus half, okay, minus half into, so algebraic sum of fixed end moments at joint A plus algebraic sum of M double dash, M double dash. So what is M double dash? M double dash is nothing but the rotational contribution or the rotational moment at the far end. So even I can write this as minus half, if I take it on the other side, it will be minus 1 by 2. So this will be summation of fixed end moments at A plus summation of far end rotational contribution, or you can say rotational moment, right. Now I need to determine these in detail. Okay. So from the slope deflection equations we have one term, that is the rotational contribution, rotational moment m is equals to what we have earned, it is 2 EI by L into theta, 2 EI by L into theta, that is the rotational moment as per the slope deflection equations. Now what is I by L? I by L is nothing but the relative stiffness, which we have studied in detail in the second module, that is in the moment distribution method. So I by L I can write it as 2E I by L, I can write it as theta into K into theta. K is nothing but the relative stiffness. Here K is relative stiffness. You have studied the relative stiffness in detail, and even you know how to determine the value of K depending upon the how is the far end conditions. Okay. Now here I want to determine the rotation factors, means how much rotation factor has to be contributed to each joint. So to do that, what I will do, I will consider one value, let us say m dash AB, means I want to determine how much is the rotational moment particularly for this joint. Then as per our equation, okay, so this value, okay, rotational contribution, it will be 2 EI by L, that is I value is also for AB span and L is also for AB span, and also theta is at the joint A, right. This I can write further 2E I by L, it is nothing but relative stiffness of the member AB, KAB into theta A, right. Let us assume that in this situation, as like this, there are many joints at the many members at the joint A. If I want to determine the total rotational contribution or the total rotational moment at the joint A, then what I need to do, I need to take the summation of all the rotational contributions of every member. That is, if I want to determine the summation of moments, that is this value m dash rotational contribution, okay. So that is also nothing but here it will be 2E into summation of stiffness of all the members at this particular joint into the rotations, into the respective rotations, okay. Now here see here, let us say it is a general equation, that is m dash. If I divide this by the all members, that is the rotational contributions of all the members, then it will be, see, 2 EI by L. So it is nothing but 2 EI into, it is K theta divided by, this is 2E, sorry, I doesn't come here, into K into theta. So here it is summation of K. So now the rotation contribution divided by the total rotation contribution at any joint it is, so everything will cancel, will remain with k by summation of k. So it is k by summation of k. This k by summation of k is nothing but the distribution factor what we have determined in the moment distribution method. But here I am interested in the rotational contribution, that is how much rotational moment has developed in each member. So this is nothing but it is k by summation of k into, if I take it on the other side, it will be algebraic sum of rotational moments of all the joints, right. So what is this value? So we have determined this here. We have determined the total, the summation of rotational moments at any joint is nothing but minus half of the fixed end moments at all the joints plus the far end rotational moments. If I substitute that value here, so it is k by summation of k into minus half of algebraic sum of fixed end moments at any joint plus the summation of the far end rotational moments. So this is the equation to determine the rotational moment at any joint. Okay, we will use this. Okay. Right. If I simplify it further, okay, so k by k, if I take it this on outside, okay, so m dash, so minus half of k into summation of k into summation of fixed end moments at any joint A plus summation of m double dash. So this term, that is minus half of k by k, k by summation of k is nothing but the distribution factor, minus half of k by summation of k, it is nothing but the rotational factor. So based on the rotational factor, we will develop how much is the rotational contribution. So therefore we will come out with an equation to determine the rotational moment or rotational contribution, m dash is equals to, it is minus half of k by summation of k into the summation of fixed end moments at any joint plus the summation of far end rotational moments or rotational contributions. So this term we will call it as the rotational factor. So therefore rotational factors, we represent it as u is equals to minus half of k by summation of k. So we need to use these two formulas to determine the rotation factors. U is equals to k by summation of k. K by summation of k is nothing but the distribution factor. Even you can write this as minus half of distribution factor also. It can, if you want, you can write this also. Right? And to calculate the rotational contributions, we need to use this formula, or even you can write this as m dash is equals to u into summation of fixed end moments at any joint plus summation of rotational contributions at the far end. So this you need to remember, this is far end. To calculate the rotational moment or rotational contributions at any joint or at any end, we need to take this equation, that is the rotational factor into the algebraic sum of fixed end moments at that particular joint into, or sorry, plus the algebraic sum of rotational contributions from the far end. So, we need to consider from the far end rotational contributions into the calculations. Okay. So, if I go with this and generalize the procedure of Kani's method, it will be something like this. Okay. See, this is the general procedure. So, in the first step, as usual, we will calculate the fixed end moments. Calculation of fixed end moments of each span. For each span, we need to calculate the fixed end moments. That is the first step what we need to follow. The second step, that is the second thing what we need to do in the Kani's method is we need to calculate the calculation of relative stiffness. So, relative stiffness is nothing but the value of K and the rotational factors. Rotational factors is nothing but U. So, we need to work out these two things, right. The third step what we need to do here is we need to calculate the rotational contributions at each joint. That is, we need to compute computation of rotational contributions. Rotational contributions are nothing but moments due to the rotation. Rotational contributions using the formula m dash is equals to u into summation of fixed end moments plus summation of m double dash. M double dash is nothing but moments due to rotation at the far ends, right. So, but whenever we are doing this or whenever we are doing this, initially in the first cycle, the far end rotational moments will be 0. And we have to keep on doing this iteration. It is an iteration process. The step number 3, it is an iterative procedure. We need to keep on finding the rotational contributions for each joint repeatedly, iteratively until we reach the same values in the next cycle also or in the previous cycle also. Means in one cycle we will get some value, in the next cycle also if you are getting the same values, then we need to stop the iterative procedure. So, here one thing you need to keep in mind, whenever we are determining the rotational contributions, the rotational contributions are calculated only for the intermediate joints. The rotational contributions here, rotational contributions are calculated for intermediate joints only. Means we are not calculating the rotational contributions for the ends, whatever may be the end. So, we are not worried about the ends, we are calculating the rotational contributions, or we are trying to balance only the intermediate joints. And this procedure has to be repeated until we get the same values. The iteration process is carried. The iteration process is carried out till we get values, till we get the values almost same as previous cycle, means until we get the same rotational moments values, we need to keep on repeating the cycles. Once we get the same values, then we have to stop the cycle. And the last step is we need to determine the final end moments. So here we need to calculate the final support moments that we can calculate. For example, if I want to calculate MAB, then it is MFAB plus 2 times the rotational moments at the near end plus 1 times of the rotational moments at the far end. So here we are MAB and MB, or you can say it is M dash B, or sorry, MAB only, okay, M dash B. So this is a formula to calculate the final end moments, or even you can summarize it as final end moments is equals to fixed end moments plus twice the rotational contribution at the near end and 1 time of the rotational contribution at the far end. So this is how we need to calculate the final end moments. Once we have the final end moments, then the next thing is the simple procedure, that is we need to go for the determining the support reactions and the maximum bending moment. So with the help of those values, we can draw the shear force and the bending moment diagrams. So this is how the Kani's method is. Okay. Thank you.